Hi, I'm Thomas Leonard, and I've recently been looking at the new effects system proposed for possible inclusion in OCaml. In this talk, I'll be giving a brief introduction to effects, and then reporting on our experiences using them over the last few months. Just to put this into context, there are three branches of work going on here. There's the domains work, to allow using multiple cores simultaneously, the runtime effects system, which this talk is about, and the typed effects system, which I won't be talking about at all. Support for multiple domains and for runtime effects are both in the multi-core repository, and you can install them with OCaml today. The structure of this talk is going to be a brief introduction to effects for people who aren't familiar with them, then an example using effects to simplify the Angstrom Parser combinator library, and finally a look at EIO, a new effect-based concurrency library. Effects are essentially resumable exceptions. You declare an effect in much the same way as you declare an exception, as you can see here. The difference is an effect also has a return type, and that is the type of the value that will be passed back to the code when the effect is resumed. So here's a simple example program, just prints step 1, step 2, step 3. We enter a try block, we print step 1. We perform an effect, very much like raising an exception. So here we use foo2 as the payload. That is handled by the nearest enclosing handler. But unlike with an exception, we also get this continuation value k, which we can use to resume the code later. And so here we'll print step 2, and then we resume the effect, passing in the value 3. Which comes back to here and becomes the value of x, and the program continues. And this example is fairly useless. We could just have used a function here. But what's really powerful about effects is you don't have to resume the effect immediately. You can store it somewhere, or return it from the try block, and you could then resume it much later, or resume a different continuation first. And this makes it really easy to use effects to build schedulers for running cooperative lightweight threads concurrently. It gives you the ability to have multiple OCaml stacks active at once, even on a single core. And this allows us to write concurrent code just the same as we would write sequential code. And you might ask why we need to do that. We can already do that using LWT. But there are some nice benefits to using effects. It ends the distinction between sequential and concurrent functions. So a lot of OCaml libraries at the moment provide a sequential version and an LWT version, and maybe an async version as well. But with effects, you can just write one piece of code and have it work in all cases. You don't need a special monadic syntax, and it means you can use all the standard features of OCaml in concurrent code. For example, if you're using LWT and you want a try block or a while loop, you can't. You have to use equivalents provided by LWT. And that's fairly simple, but it would be nice to be able to use the language's built-in features directly in concurrent code. Using effects is also faster, because we're not using the heap to simulate a stack. And having a real stack means that backtraces and profiling tools work properly too. So that's a very brief introduction to effects. Let's look at how they can help in a real program. So Angstrom is a popular OCaml library for writing parsers. It's designed for concurrent applications such as network services, and it has a really strong focus on performance. So as a warm-up, let's look at a toy parser first. The idea here is we've got some input stream of characters, and we'd like to read a value from it. And in this very simple toy parser, we'll say that an alpha parser is just a function that takes the state of some input stream and produces a result value of type alpha. Here's an example of a primitive parser, anychar, which just reads one character from the stream. First of all, we're checking that the buffer contains at least one character, and maybe at this point we'll stop and wait for some data to come in over the network. And then we get the character, we update the state of the input stream, and we return the character as the result of the parser. And the idea is that these simple parsers can then be combined. For example, this right star combinator combines two parsers, A and B. First of all, it parses with A, then it throws the result away, and then it parses with B and returns that as the result. Maybe A consumes some white space and B parses the actual value we want. And that's fine if you want blocking code. The problem is if you want to run, say, a web server, and you don't want your whole system to stop running, waiting for data from one request. You want to be doing other things while you're waiting. And because of that, real parsers can be more complicated. So now let's look at a real parser, Angstrom. We'll look at the equivalent to this type. So instead of saying that a parser is a function from a state to an alpha, Angstrom says this. You don't need to read all this, but what I want you to notice is that it's got more complicated. Roughly speaking, a parser in Angstrom is a function that takes the state of the input stream, a continuation to call if the parse fails, and another continuation to call if the parse succeeds. And it returns, well, it might return success and the value you parsed. It might return failure, but it might also return this partial state. And that indicates that Angstrom didn't have enough data in the buffer to be able to parse your value. The application code now needs to get that data somehow, put it in the buffer, and when it's ready, call this continue function to resume parsing where it left off. And using this API, we can define any char. It's a bit more complicated than before, but here it is. It takes the state of the input, the failure continuation, and the success continuation. And in the case of any char, it always succeeds, so it calls the success continuation with the character it read. And in the case of the right star combinator, we run A with a modified success continuation, which discards the parsed character and then runs the B parser. We could have made this code look a bit nicer using a monad, but that would also have a slight performance cost, so Angstrom writes everything in this callback style. And so we got to thinking. A lot of this complexity is about trying to suspend parsers, and this is something that effects can allow us to do very easily. So we made an effects branch of Angstrom, and this is what we came up with. Well, this is just the toy example I showed you at the beginning, because that is exactly what you can do when you have effects. On the effects branch, a parser really is a function from an input state to an alpha. In fact, I didn't have to use any effects at all to implement this. You could run this branch on an ordinary non-effects version of the compiler, and it would just be a boring blocking parser. But when you set up this state parameter, you provide a function to refill the buffer. If you provide a function that performs an effect, and you run the parser within an effect handler that implements a scheduler, then you now have a concurrent parser. And Angstrom itself doesn't need to be changed in any way to support that, which is pretty nice. Okay, so that's a lot simpler, but what about performance? Here's a micro benchmark. The parser we're using here is skip many any char. Skip many is a combinator that just runs its argument repeatedly and throws away the result. And we're processing some long string here. These are results from core bench. And we can see that using the effects branch, it's 13 times faster than upstream Angstrom. But perhaps more interestingly, when I was doing the conversion, once I'd written the skip many combinator as plain OCaml code, it was really obvious that it wasn't tail recursive. And it was also really obvious how to fix it. So for a slightly more fair comparison, I went back and I modified Angstrom with the equivalent fix. And with that change, we're only 3 times faster. That's still pretty good. You'll also notice that the effects version doesn't allocate any memory, or at least it doesn't allocate any memory on the heap. It's only using the stack. This benchmark's nice, but it's not very realistic. People don't really write parsers that parse individual characters because the overhead is pretty high. A more realistic parser is parsing an HTTP request. And this is one of the benchmarks in Angstrom's test suite. And here we've gone from 60 milliseconds with the original Angstrom to 50 milliseconds with the effects branch. And we've also gone from 102 kilowords to 600 words allocated on the major heap. It's not a huge speed up, but it's quite impressive for a well-optimized library like this. So it's a little disappointing that we haven't actually used any effects yet. I mean, just the mere fact that effects exist allowed us to make all these simplifications. But I did find one place in the code where it was actually useful to define and handle an effect in Angstrom itself. And that was to provide some backwards compatibility with the old API. Angstrom has an existing buffered API that provides a simple abstraction for feeding data in. The effects version of that API is much simpler, but to avoid breaking existing software, I wanted to continue offering the old callback API too, while internally using the new effects-based parser. And this is the simplified version of that code. I define a read effect to be called when Angstrom needs more data, and then in the parser itself, we create the buffer as before. We call the effects-based parser, passing in our read function that performs the effect. And when Angstrom needs more data, our effect handler is called. And that returns the old partial object to the application code the same as before. The application then fetches some data itself, and when it's ready, it calls this continuation function, which then continues the effect. So the user just sees the old callback-based interface, but internally we're still using effects and getting the performance benefits of that. The refill event happens relatively rarely, so this callback wrapping isn't performance critical anyway. So in summary, using effects here made the code go slightly faster, but more importantly, it made it much, much simpler. We didn't need to use any effects at all in the interface, or in the main implementation. We only used them in the backwards compatibility layer. The public API looks very similar to before, except now it looks like we also offer a simple synchronous API. Except that with effects, that synchronous API can also be used asynchronously. And combining effects code with callback code is also very straightforward. Now, so far we've been assuming the existence of some concurrency library using effects, and I'd like to talk about that next. We've been building an effect-based alternative to LWT or async called EIO. It provides a generic API package which performs effects and that libraries can program against, and then there are various backend packages that handle the effects. We've got two backends at present. There's a libuv one that works on Linux and macOS at least, and probably other backends, probably other platforms as well. And we've got a high-performance IOU-ring backend for Linux. IOU-ring is a new way of writing applications for Linux where you share a ring buffer with the kernel and write the operations you want to perform there. Linux performs them asynchronously and writes the results back to another ring buffer as they become available. And that avoids the overhead of using syscalls. So here's an example of a little EIO program. This is a web server. Here we're using the HTTP AF library, which is a nice high-performance HTTP library using Angstrom to parse requests. And we've modified it a little to work with EIO. And this setup is essentially the same as you'd have with the LWT version. Then we've got the main function, which takes access to some network as an input. It creates a listening socket on some host and port. And then in a loop, it accepts connections and handles them using the handler. And we can see that this loop is written as a normal OCaml while loop. There's no need for any special library function or PPX here. So how does EIO perform? Here's a benchmark. We're using the work2 load testing tool to open 100 concurrent connections and then make requests as fast as it can on those connections. On the horizontal axis, you can see how fast it wanted to issue requests, and on the vertical axis, how fast the servers were able to go. At the bottom, we've got LWT with the co-HTTP library at around 40,000 requests per second, and then Go is a little higher at 60,000. We can go quite a lot faster by using LWT with HTTP AF instead of co-HTTP. That's around 130,000 requests per second. And using AEIO, which is a very simple effects-based library that reuses parts of LWT, we get around 140,000. Then near the top, at around 190,000 requests per second, we have Rust with the Hyper framework. And right at the top, at about 200,000 requests per second, we have HTTP AF with EIO. I should say this benchmark is a little bit cherry-picked, because if you run this with 1,000 concurrent connections instead of 100, then Rust is first and EIO is second. And also, Rust has recently released their own IOU-ring version, and we haven't benchmarked against that. So I suspect Rust will soon be in first place again. But in any case, effects give OCaml very competitive performance, and much better than we've had before. I should also say that in these benchmarks, we limited the servers to 1 core, because some of these servers can only run on 1 core. But Rust, Go, and EIO can all use multiple cores when available for a nice speed up. Before I wrap up, I'd like to mention a few other interesting features of EIO. It uses structure concurrency, so you can tell from a function's type whether it can create any threads or file descriptors that outlive it. It uses the OCaml security model, so if you're writing a web server and you want it to serve only files within some directory, you can just pass the function access to that directory and it won't be able to access anything outside of it, even if the user tries to trick it by passing a path containing ... or by following a symlink that points outside of the subtree. We have tracing support that integrates with Mirage Trace Viewer, and we have support for multiple cores. The library is still very experimental, and it's not ready for general use, but if you'd like to help us refine the API, then please give it a try. To conclude, our experience has been that using effects for concurrency works extremely well, and that effects have very good performance. Even in the benchmarks, the effects system didn't seem to be the bottleneck. Now, I didn't work on the effects feature in the compiler itself, but congratulations to the people who did. I've not found any bugs in the effects system during my testing. I did find a few bugs in the multi-core support, which have been fixed, but none in the effects. It seems really robust. And if you'd like to try out the effects feature or the EIO library, there is some getting started documentation on GitHub in the OCaml multicore/EIO repository. And thank you for listening.